When a company decides to open a new facility, they're not just picking a city on the map. They're making a decision that will cost tens of millions of dollars, affects hundreds of jobs, and shape their competitive position for the next 20 years. So what goes into that decision? What factors actually matter? And once you've identified the candidates, how do you mathematically determine which location minimizes your total cost? That's exactly what we're covering today. We'll go through the key factors that drive location decisions, look at how companies structure these choices, and then build a quantitative transportation model that gives us rigorous, data-driven answer. So, location decisions are driven by a surprisingly wide range of factors. Let me group the most important ones. As you see here, one of the first, cost factors. These are the ones that hit the income statement directly. Labor cost and availability. In many industries, this is the single biggest driver. That's why manufacturing shifted from the US to the Southeast Asia over the past 40 years. And it's why now starting to shift again to countries like Vietnam and Mexico. Land and construction costs vary enormously. A warehouse in rural Ohio costs a fraction of an equivalent facility near Los Angeles. Energy costs matter, especially for process-intensive industries. A data center, for example, needs enormous amounts of cheap electricity. That's partly why data centers clusters in areas with hydroelectric power, like the Pacific Northwest of Scandinavia. Second, then there are proximity factors to customers and raw materials. For a service business, being close to your customers is often non-negotiable. A restaurant can't be 200 kilometers away from its market. For example, Toyota's decision to locate its Georgetown, Kentucky plant in the 1980s was heavily influenced by proximity to its US customer base, while also benefiting from lower labor costs compared to the Northeast. Finally, regulatory factors. Tax incentives, government regulations, environmental standards, exchange rate stability. These can easily tip a borderline location decision. When Tesla evaluated sites for the Gigafactory in Nevada, offered $1.3 billion in tax incentive. That's not a minor factor. That's a deciding factor. When we talk about facility, location decision, operations management, there are three distinct but related decisions being made simultaneously. First, how many facilities? Do we need one central hub or multiple regional facilities? More facilities mean better coverage, but higher fixed cost. Second, we look at the where. Where exactly? Given the candidate sites, which specific location minimizes total costs while meeting service requirements. Thirdly, how large? What capacity does each facility need? Overbuilding wastes capital. Underbuilding creates bottlenecks. These three decisions are interdependent. Adding a second facility changes the optimal size of the first. Choosing a location affects how large each facility needs to be. You can't fully separate them, which is why location is classified as a location allocation problem, as stated here. Before jumping straight into building a new facility, it's worth asking, do we actually need one? The most common trigger is demand growth. The existing network simply can't serve new customers efficiently anymore. Other triggers include shifts in where demand is geographically concentrated, changes in input costs like a supplier moving or energy prices shifting, and sometimes external shocks like fire, flood, and regulatory changes. But before committing to a new facility, smart companies first explore alternatives. Adding shifts over time, building seasonal inventory buffers, using subcontractors, or upgrading equipment to the existing location. A new facility is a last resort, not a first response. The capital cost is too high and the decision is too irreversible to rush. Do not rush. Now, let's get into the quantitative side. When you have multiple supply points and multiple demand points, you want to find the lowest cost way to serve all demand without exceeding any supply. That is a transportation model. Here's the setup. You have M sources, warehouse or plants, each with supply capacity SI. Here. You have N destinations, customers or distribution centers, each with demand DJ. You know the cost of Cij of shipping one unit from source I to destination J. Your decision variable, Xij, is how many units to ship from source I to destination J. Let's take a look at the mathematical model. The objective is to minimize total shipping cost. The sum over all of I and J of Cij times Xij. These are subject to two sets of constraints. These are subject to two sets of constraints. For each source I, the total shipped out cannot exceed its capacity SI. Second demand constraint, for each destination J, the total shipped in must be at least DJ. We have to meet all the demand. And our non-negativity, you can't ship negative units. That's quite the obvious. So, let's look at a real example. Let's make this concrete. Sears has plants in Albany and Little Rock and serves customers in Boston, Philadelphia, Galveston, and Raleigh. They're deciding whether to open a new plant in Atlanta or Pittsburgh. We run the transportation model twice, once in Atlanta in the network, once in Pittsburgh, and compare the total cost. The model with Atlanta gives us $7,980. But Pittsburgh gives us a higher cost. So Atlanta is the better location. Not based on intuition, but based on mathematical optimization. So here's our mathematical model summary. We minimize Z, which is our total shipping cost, and we say these are all subject to minimize Z, sum of Cij times Xij, subject to the sum of I, Xij, has to be less than or equal to Si. These are our supply constraints. Now let's solve a question together. Eco Bottle Inc. has two factories. Factory A in Istanbul, and the supply is 400. And Factory B in Ankara with supply units of 300. They serve three retail hubs. Hub 1 in Izmir, which is 250. Hub 2 in Bursa, which is 200. Hub 3 in Adana, which is 150 in demand. Shipping costs per unit are given below. Formulate the transportation model and write the GAMS code structure. First, we calculate the total supply and find that it's 700. Our total demand is 600. We see that our supply, 700, is greater than our demand, 600, which would mean it is feasible. Now, let's write the math model. We say set A, I of J, are our factories. Set J, which is our hubs. Our objective here is to minimize Z. This is all subject to supply A, this is the formula, supply B, demand 1, demand 2, and demand 3. And our non-negativity is as follows. Now, let's write this in a GAMS code. First, we write our set. We define our sets I, factories. In GAMS, you should use only one. Factories A and B. Our J, which is our hubs, are defined as hub 1, hub 2, and hub 3. Let's define our parameter now. AI is our supply. And we know that for A, we have 400 units, and B, we have 300 units. Our BJ, demand, hub 1, which is 250, hub 2, which is 200, and hub 3, which is 150. Our CIJ is our cost. So we would say A hub 1, 8. Our A hub 2 is 5, and our A hub 3 is 12. Now let's look at B. Our B hub 1 is 14. B hub 2 is 9. B hub 3 is 6. Our variables are X, Xij, and our positive variable is X. Our equations: cost, supply, I, and demand, J. For cost, we would say Z is equal to Ij, and our Cij times our Xij. Our supply, I, would be the sum of J and Xij is equal to, this is greater than, less than or equal to AI. And our demand, J, sum Ij is greater than or equal to Bj. We solve the eco bottle using LP minimize Z. After GAMS solved this, our intuitive optimal cost would be $3,900. Thank you very much.